Ever looked at your computer specs? 4, 8, even 16 cores, and just wondered how in the world all that power gets managed? Well, it's not magic. It's actually this incredibly sophisticated dance, and it's choreographed by the Windows operating system. So today, we're going to pull back the curtain and take a look at that unseen conductor that makes it all work so smoothly.
So, let's just dive right in with a question I bet you've asked yourself before. You get a brand new machine. It's got double the cores of your old one, but it doesn't always feel twice as fast. So what gives? Well, the secret isn't just about the raw hardware. It's about the incredibly clever, and sometimes pretty complex, strategies that Windows uses to actually harness all that power.
All right, first up, one system, many brains. This is the absolute bedrock, the foundational principle that Windows builds everything else on when it comes to managing all those processors.
And that foundation has a name: symmetric multiprocessing, or just SMP for short. Now, the core idea here, and it's really cool, is all about equality. In the world of Windows, there is no master processor, no boss core telling the others what to do. Think of it more like a super efficient team where every single member is equally capable of grabbing any job that comes along. Doesn't matter if it's a deep system-level task or just running your web browser.
And this comparison really makes it clear. On the left, you've got the Windows way of doing things, SMP. Any processor can do any job. Simple. On the right, you have the other model, the asymmetric one, where you've got one boss processor that handles all the important OS stuff, and the other worker processors just run your apps. You can probably see why the Windows model is built for way more flexibility and, ultimately, better performance.
So why should you care about this? Well, it's pretty simple, actually. SMP is what allows Windows to spread the workload across every single core you paid for. It's what makes sure that no part of your CPU is just sitting on the sidelines doing nothing, and that directly means a faster, much more responsive computer for you.
All right, next up, we're diving into the memory neighborhood. Because as soon as you treat all your processors as equals, a whole new, really fascinating problem pops up: the geography of your data.
I mean, just think about it for a second. In a big, complex computer, not all of your memory can be physically right next to every single processor core. It's just not possible. So what happens when a processor needs a piece of data, but that data lives in a memory bank way on the other side of the motherboard?
Well, this hardware reality is called non-uniform memory architecture, or a NUMA, and the city-neighborhood analogy is perfect. It's way, way faster to run down to your local corner store than it is to drive all the way across town for a gallon of milk, right? Same idea here. A processor can snatch data from its local memory super fast, but getting it from remote memory, well, that takes longer. And that time difference can become a huge performance bottleneck if you don't manage it properly. So how does Windows solve this tricky problem? It doesn't fight the geography, it maps it. When your computer boots up, Windows does this detailed scan of your system's hardware layout. It figures out exactly which cores are on which chip, which memory banks are closest to which processors, the whole shebang. And based on that map, it logically sorts them into these things called processor groups.
And this, right here, is why it all matters. Because Windows understands these hardware neighborhoods, its scheduler can make really smart decisions. It actively tries to keep a running task and the data it needs to work with on processors that are in the same group. That simple idea of keeping things local is absolutely the difference between a lightning-fast operation and a really annoying stutter in your favorite game or application.
Okay, so Windows can use all its processors equally, and it knows how to keep data close to the right ones. But there's one more massive challenge. With hundreds, maybe thousands of tasks all running at once, how does it play fair?
I mean, picture this. You're rendering a huge video file in the background. That thing is hungry for CPU power. But you still want to be able to move your mouse smoothly, maybe type in an email, and have your music not skip a beat. So how does Windows stop that one heavy-duty process from just taking over and bringing the entire system to its knees?
The solution is a really elegant system called Dynamic Fair Share Scheduling, or DFSS. The best way to think about it is that the OS acts like a very strict, but very fair, manager who's handing out a budget of CPU time. DFSS automatically groups related tasks together, and then it makes absolutely sure that no single group can just monopolize all the processors, leaving nothing for anyone else. It's all about enforcing balance.
And this isn't just some abstract theory either. The system gives you real tools to enforce this. You can literally bundle a group of processes together into something called a job object. Then you can set specific CPU limits for it. And from that point on, the scheduler becomes the enforcer, making sure that job never, ever goes over its assigned budget.
At the end of the day, DFSS is pretty much the unsung hero of multitasking. It's the mechanism that's constantly working behind the scenes, making sure that your mouse cursor and your web browser always get their fair slice of the CPU pie, no matter what else is hammering this system. It's why your computer still feels responsive even when it's working really, really hard.
So when you put all of these pieces together, you really start to see this beautiful, elegant system. It's like this powerful, unseen conductor, making sure that every part of your computer's hardware orchestra is playing together in perfect harmony.
So let's just quickly recap those three big pillars we talked about. First, you've got symmetric multiprocessing, which says all processors are equal partners. Second, you have NUMA awareness and processor groups, which solves that tricky data geography problem. And third, dynamic fair share scheduling, which acts as the great equalizer, making sure the whole system stays stable and responsive for you.
And that kind of leaves us with one final big thought. We're heading into an era of ridiculously complex processors, chips with different kinds of cores, some built for raw power, others for efficiency. And that completely changes the game. As our hardware keeps evolving, the very definition of what's fair and efficient is going to have to evolve right along with it. And that, right there, is a fascinating challenge for the operating systems of the future.
Help me out, please smash that like button, leave a random comment and subscribe if you want to become a better hacker.